Thank you very much. So, as you may or may not know, today is Midsummer's Eve in Sweden. And this means that all over the country they're putting up these maypoles, and everyone is putting on their folk costumes and they're dancing around the maypole like this. So, to understand Swedish Midsummer as a computer scientist, you should think of the maypole as a shared resource that all the Swedes want to access. Now, recently we've been having some scalability issues. We passed the 10 million Swede line, so there's a lot of contention, a lot of stepping on each other's toes around these things. So a few years ago, the Swedish government said that from now on we'll use a lock-based scheme, so only one Swede allowed near a maypole at any given time. And this wasn't, of course, very popular because most Swedes just had to wait, and it's not very fun being there on your own. So instead, what they did is they started teaching these choreographies, these special dances that allow Swedes to dance around the maypole in a synchronized manner like this. The most popular one being Små grodorna är lustiga att se, which roughly translates to lock-free programming. And I'm not going to go into the differences between sort of non-blocking, non-waiting, I'm using the term a bit sloppily here to just mean some kind of fine-grained concurrency that is achieved by following some protocol that assures synchronization. And often this protocol follows the pattern of reading some shared value and performing some local computation on that value, and then if the speculation is still valid, then you try to make your value global. You try to publish that value. And in order to do this without locks, you need some kind of atomic primitive, and one of the most common ones is the compare and swap operation, who in pseudocode looks something like this, that you compare the first and second arguments, and if they are the same, then you assign the third argument to the first argument. And the important thing here is that the comparison and the assignment are performed atomically. So let's have a look at a lock-free data structure. This is a very classic example. This is a lock-free stack by Treiber. So we have some struct. Var just means that it's a normal mutable field. Val is a value field. So there's a stack head and there are stack nodes, and each node has an element which is some elided type T. So if you want to pop from this stack, a thread will come in and it will read the top field, and another thread might come in and do the same thing. And then this green thread is now going to compare these two and say, if my speculation here is valid, if these two are the same, then I want to overwrite s.top by oldtop.next, like so. And now the thread can read this element. So now the purple thread will come and try to do the same thing, but now of course s.top, which is this one, and oldtop, which is this one, are no longer the same. So this comparison will fail. So the purple thread will have to restart, make a new speculation, and then try again. Another similar structure is a queue by Michael and Scott, which is similar, but there's a last pointer now, and all the fields are mutable. So I won't go through it in detail, but if you want to enqueue something, you start by creating a new node, you read the last pointer, and then you try to update the next pointer of the last pointer to create a new one. And in this particular data structure, it might be the case that there's another thread coming in trying to do the same thing. It will fail because the speculation is no longer the same as before. This will fail because old last.next is not equal to null because it's been written to. But then it's the purple thread that actually updates this. So the point I'm trying to make here is that as you can imagine, getting this right can be quite tricky, which should be obvious from the amount of arrows going everywhere on this. And this sort of symbolizes that at any point in time, there's an unbounded number of threads accessing this data structure at any point in time. But even though there are a lot of things happening, we can still find some common patterns between these algorithms. So, for example, in both examples, we read some value speculatively, even though we knew that this value might be changed by someone else, but we still read it, and then if the speculation is valid, we will do something with it. In the enqueuing part, we created a new node, and we tried to publish it. The same thing would go if you wanted to push to the stack. When popping, we're sort of extracting a node from the data structure, and we're so that we assert ownership over it. And the same thing would happen when you dequeue from the queue. So the idea of this work is to give these concepts types, which mean something. And not only do we want types that capture these concepts, but we also would like a type checker that can tell us that, hey, this field is subject to races, so this thing can't be right. You have to write to it using an atomic operation. So we should just stop and think of why should we use types. So there are systems now based on there are model checking tools, there are things based on concurrent interpolation logic that can basically prove these algorithms correct automatically by now. And it's a trade-off between reasoning power and simplicity, really. So with a type system, we can just look at a single line of code, and the types will tell us something meaningful. So we don't need to look at all the threads that are going on. We can just look at a single procedure and learn something from it. And also, it's about increasing language expressivity. So in the end, what we're going to end up with is a type system that allows us to have a concurrent data structure that stores linear or unique references. And even though there is contention on this thing, we can still guarantee the uniqueness of these things. So uniqueness or linear references are interesting because they sort of give a very simple way to reason about ownership. So what I mean by linear reference is the only reference to an object in the system. So if you're holding the reference, there is no one else that can access it. And if you want someone else to access it, then you can just transfer it to someone else, and that thread will have access. So it makes ownership very explicit. So if we think about lock-free data structures for a while, a correctly implemented lock-free stack, for example, can ensure that at most thread will manage to pop the first element, which seems similar to what's going on here. So the idea here is, can we use linear types somehow to capture this thing? So let's go back to the stack and see how it would work. And immediately we see some problems because we have sharing of this stack between threads. They may be accessing at the same time. And even in the single-threaded case, there's aliasing between different nodes like this. So just vanilla linear references won't work out of the box. So the first thing we do here is that we relax linearity. So we say that it's okay to have any number of aliases to an object, but at most one of these aliases may have ownership. I will get back to what I mean by ownership in a little while. And the point is then that this ownership can then be atomically transferred between aliases like this. So here you can see if the label 1 means that this is an owning reference and 0 means a non-owning reference, then the sum of the labels of all the incoming pointers will always be at most 1. And this is similar to capability systems, but we're going to want to be able to transfer these things without taking locks and without sort of stopping progress for another thread. So the way we're going to do this, as you might have guessed, is to use the compare and swap operation. But since we're going to impose certain syntactic and restrictions and reasonable types, we're going to call it compare and transfer. So dynamically, a compare and transfer has exactly the same dynamic semantics, but when we think about ownership, this is going to mean we're going to transfer ownership of x.f to y and from z to x.f. So the intuition here is that x.f contains the only owning reference in the system. And since we are overwriting this reference, so this reference is going away, it's safe to transfer ownership from this thing to something that we know is an alias of this object, namely y. So we do this sort of castling move. So I'll go back and just show it one more time. So transferring ownership of x.f to y and from z to x.f, like this. So let's see how this might look in practice. So here we're back to the good old stack. a thread comes in and looks at old top and gets a non-owning reference. And then it tries to say, okay, let's transfer ownership of s.top to old top, and we will say that this is okay because we're overwriting s.top with whatever is in old top.next, like so. And now it's safe to extract the element from the node. What's interesting to note here is that this reference is still in the system, the next node of the next field of the node that we just popped. But this will now be a field, a reference without ownership, and this is something that we're going to track in the type system as well. So what we saw more in general here was a compare and transfer operation to unlink an object from a chain of objects. So here we have a chain ABC, and we want to unlink B. So what we do is we transfer ownership of x.f to y, like so, and this thing is safe to do because at the same time we're going to transfer ownership, we're going to replace this thing by the ownership that was in y.g. Similarly, we can go the other way. When we have an object that we want to insert into a chain of objects like this, we're going to transfer ownership from x.f to y.g, and then from y to x.f. So this gives us 3 syntactic variants. These are the syntactic variants of the cat operation that we allow. And so far this has been enough to express the things that we've tried to express. So we're doing linear ownership with a lock-free compare and transfer operation. And we make sure that we're following these protocols correctly through a type system that we call lolcat. So in lolcat, ownership means that it holds permission to access the mutable fields of an object. So the top field, for example, holds the only permission to access the mutable element field here. Any thread can access this immutable field because since it's immutable, there will be no races, so we're fine with that. We're also going to mark certain fields as being contended, so we're going to allow races on this field explicitly and say that this thing may be updated at any time, but it must be updated atomically. So we mark it with the keyword spec in the sense that it's any value that you read from there is speculative. So it may change underfoot at any time. And this also means that we can have any number of references to this thing, because the only thing that you can access is something that we've said explicitly that we allow races on. And then we're going to use flow-sensitive types to track this ownership. So once again, the pop example. When we read old top, we're going to get an alias of the type node bar elem. This means that we've restricted the field elem, and we're not allowed to read the element field. And there may be several of these aliases. And when this compare and transfer succeeds, and we transfer ownership from s.top, we're going to change the type of old top in the branch, in the then branch, to this type, node till the next. And now the element field is no longer restricted, so we can read the element field, but we've marked this to say that the next pointer is now a reference without ownership. So in general, a reference of type node can access the full node. A reference of type node bar elem has the element field restricted and cannot access the element field, but these two aliases may coexist. And a reference of type node till the next, it can access the var field elem because this is no longer restricted, but it knows that this field is without ownership, so we're not going to try to extract ownership from this thing because the only ownership lies in this field now. And through a combination of static and dynamic techniques, we make sure that no other threads are going to succeed with this either. And the main invariant here is that for all aliases of a node, at most one of them has ownership of the var field elem. Okay, so once again, let's go back to the stack. Here's what we said. So how does this look if we add types to if we add our lolcat types to this? Well, here are the changes that you need to do. You need to mark the top field as being the contended field of the struct. And you need to change the compare and swap operations to compare and transfer, and that's it. So all of the other types can be inferred. So if you do this with recursion rather than loops, then you would need to write the types in the argument, in the parameter list. And the same thing if you wanted special types here, then you would have to write them. But locally, all the types can be inferred. If you want to, you can be more explicit and you can mark which reads are speculative reads and which reads are these reads that actually move ownership. You sort of with consume, which could be a destructive read, for example, and speculate being a speculative read. And this can be nice when you're actually programming this thing, but we don't need it. They can always be inferred as well. So in the paper, we've formalized lolcat for a simple procedural language. There are a few additional constructs for reasoning about stable fields and object initialization. So if we go back here, we'll see that the next field is a val field, but we're actually writing to it here and here. And this is because we're tracking that we just created this thing, so it's actually globally unique, so it's safe to update this until we manage to publish it, and then this thing will be immutable. So this is similar to constructors that may write final fields in Java, for example. And the main property that we're interested in here is the linear ownership. So at most, one alias may access the var field of an object at any time. We've used this language to implement 3 lock-free data structures: the Treiber stack that we saw, the Michael Q. Scott from the beginning, and the Tim Harris list. And there's also a prototype implementation which is in the language Encore, and this is an object-oriented language. There are some interesting things relating to self-typing and encapsulation that shows up when you move to an OO setting. Things that we've done since we've submitted the paper, but it's not in the actual paper, is that we've implemented other things in Encore. There's a skip list, there's a binary search tree set, there's a lazy list-based set by Heller, and this is interesting because this actually contains a lock. So it uses locks, but we don't need special support for locks, but we can implement the locks themselves in lolcat as well. So this is interesting. And we believe that we can do lock-free hash tables and handlers elimination back of stack, but we need support for arrays, so we're sort of blocking on that. Another direction of work is done by my colleague Albert Yang, who leverages the types of lolcat to create a pluggable concurrent garbage collector. So you plug that on top of another garbage collector, and you use the types to track when you can collect objects. So if you're interested in this, then you should have been at ISMM this Sunday, but you can still find Albert in the lunch break and ask him about it. So we presented this idea of relaxed linearity, where access to var fields is always exclusive, but we have controlled sharing of certain fields, these immutable fields and the contended fields, and we use compare and swap operations to transfer ownership between the aliases. And this way we can guarantee data race freedom in lock-free data structures, except for, of course, the places where we allow it. And this is an open source implementation, so if you ask me for the correct feature branch, then you can try it out when you get home today. So I'll just say happy midsummer, and I'm happy to take questions.
Okay, are there any questions?
Thank you. All right, this is very nice. Do you assume your language to be garbage collected?
Very good question. So our language should be with garbage collection, it should work fine. Of course, you have to make sure to avoid ABA problems, but there would be there's nothing special that you need to do for this system that you couldn't do in, say, Java or some other language that is garbage collected. So since we're more or less only doing the static things anything that you could do for existing implementations with respect to memory management, you should be able to do here as well.
All right, then the related question. So in non-garbage collector languages like C++, people implementing fine-grained data structures typically rely on mechanisms like hazard pointers to make sure that the memory reclamation is safe. And I wonder whether your approach scales to prove the safety of such algorithms.
Oh, if we could use the types to ensure safety of the actual hazard pointers, or if we could use hazard pointers to, on top of this, to have safe.
Well, can your type system establish the absence of ABA problem and race freedom in the presence of manual memory reclamation and hazard pointers?
So I don't think that the system itself would help to, it wouldn't make it easier to avoid ABA problems, but at the same time it wouldn't make it harder. So anything that you could do in C, you could add on top of this and it should work, I believe.
The answer is yes.
Have you tried it?
No.
The garbage collector that he was talking about uses ECOOP-based reclamation scheme, and we can know exactly when to insert the proper instructions to make it work. So if you use a fully manual technique, for example, using some form of counter to avoid the ABA problems, you can just insert those automatically by just looking at the types in the code.
All right, thank you.
So really, if Albert was in the room, I would have passed it on to him. But yeah, go ahead.
I find this work very impressive, and thank you for the very nice presentation. I was wondering whether you have got, whether your system would have the following property. You take a program that type checks with your type system could be transformed to an equivalent simpler program where you perhaps throw out some of the loops and some of the cat statements. So an equivalent program that would have not consider concurrency and would have the equivalent behavior. So taking the example, do you understand what I mean?
So you mean that we could have something, if we know that we're not going to be accessing it concurrently, then we could do it cheaper because we wouldn't have to use the
No. I mean, if I want to understand your program, which has got the loops and the casts and so on, I put it through a filter that throws away some of that stuff and gives me the program that has got the equivalent semantics sequentially. So I read it sequentially, understand it, but then I am sure that it works correctly in the concurrent setting.
Yeah, I see nothing that prevents such a transpilation. I think that could work.
Okay, great. Thanks for the good questions, but now we have to switch over to the next talk. So thanks again to Elias.